Okay, so here's an example of an implementation of a ray tracer. And it's a little slow because I implemented something called soft shadows, which I'll talk more about later. But so it's going real time here, which is cool. So this is using a particular perspective, just like I was before. So I can do the same sort of thing where I increase the field of view in Y, like that. But also there's an option to do orthographic. And here's what orthographic looks like. It looks super weird as you move around because we're not used to seeing this way. But what orthographic does do, which is very useful, is it doesn't warp the geometry. So no matter how far away something is, it will appear at a size which is its actual size. So these two spheres are actually the same size, the one with the checkerboard and the other one. If I look at them from perspective rendering, it looks like this one's bigger because I'm closer to it. But if I switch back to orthographic, you'll see they're the same size. And I can also see that this box is twice as big as this one, which is a little bit harder to see from perspective. And also I can see that this ellipsoid, I know it's mostly black, but this is an ellipsoid that is twice as wide as these spheres, which again is kind of hard to tell. It really looks like from perspective that this sphere is the biggest. Okay, now one last thing I want to mention, and then there will be just a very brief exercise in JavaScript. A cool thing about ray tracing is that we can deal with ray intersect objects that aren't just triangles. So I told you with the object first renderer, everything is a triangle at the end of the day. We had to, even for the complex shapes, we had to divide them up into triangles and stitch them together to approximate those shapes. But we don't have that limitation in rays. If we know how to intersect a ray with something, then we can model that something. We're not limited to triangles. So this is why I taught you how to intersect rays with spheres. So we can actually get an exact solution. We're not approximating anymore. Of course, up to numerical precision, but we don't have to try to model a sphere with a bunch of triangles stitched together. We can model a sphere as a true sphere at all scales with a ray tracer. But one thing is, now you'll see, now that we're talking about lighting, we actually need to know the normal at the sphere, right? Because the normal is what determines how light reflects off of this thing. So basically everything that's continuous, if you zoom in far enough, it'll look like a line segment. Or in the case of a 3D sphere, a plane. So what that means is I can actually, it's meaningful for me to say that it has a normal locally. What it's like saying is I can fit this tangent here to the sphere. It would be a tangent plane in 3D. And that the normal is what's perpendicular to that. Okay. So we went ahead, and in mini assignment 1, we learned how to intersect a ray with a sphere and get the point of intersection. But we didn't learn how to get the normal. So I'll call this P, and then I'll call this the normal N. But actually, this is relatively easy compared to finding the intersection. The intersection is the hard part. Once you find the intersection, all you have to do is make the following observation. So this is the center of the sphere. And it turns out the normal at any point on the sphere can be obtained by just subtracting the point of intersection from, subtracting the center from the point of intersection. So you construct a vector like this. And you see this vector actually points in the direction of the normal there. So that's one kind of neat thing about the sphere, is that the direction to the point from the center also happens to be the direction of the normal vector. So all you have to do is subtract, so we'll say n, the normal, is equal to, it's the vector which is p minus c over the magnitude of p minus c. Because we want the normal to be a unit vector, so we're going to divide by that length. So that's all there is to it. So I'm just going to want you to implement that real quick in JavaScript, but you'll be implementing it actually in GLSL for the ray tracer.